So let's start. In the last couple of classes, we have been looking at the telescopic cascode, and the idea was to have a PMOS cascode. Let me draw it quickly once. So here we have the PMOS current source, and then we added a PMOS cascode. We also had an NMOS cascode, and then the NMOS diff pair. So this was the complete thing. And to get a single-ended version, we basically did this diode connection thing, right? So this was the telescopic cascode. And in the last class, if you recollect, we also saw that we can generate this bias voltage for this cascode by just doing this kind of diode connection. But what was the problem? It had a limited swing compared to doing this. Okay, great. So as we saw, this gives a gain of the order of GM R0 square. It's good. But what was one issue with this? Yeah, it had a limited output swing. Okay, and especially that becomes severe when you try to put it in unity feedback like this, right? And we computed, so let me reuse those results. So we saw that the ranges were this, right? And the swing finally was only limited to this. Okay, so let me rewrite them. So I have to rewrite it, VB4 minus VTH4. The minimum was VB4 minus VTH4, sorry, the maximum, and the maximum is VB4 minus VTH4 plus VTH2. Right, this was the minimum, this was the maximum, and the total range was just a threshold minus an overdrive voltage. And to give a rough example, even if threshold is say 0.4 volt and overdrive voltage is say 0.05 volt, we get only 0.35 volt of swing, irrespective of what your VDD is, right? If your VDD is 1.2 volt, you are losing almost 1/4 of the swing. Okay, great. So in this class, we'll look at another variation of this cascode implementation. Okay, and again, we'll start with a single-ended circuit because we know even for the cascode, telescopic cascode, we started with this fellow, and then we made the differential. So we'll do the same thing. And in the telescopic cascode, we have the NMOS acting as the current source or the VCCS. So it generates a current GM delta V in response to the increment you apply, and this current was basically buffered by this common gate, and at the top you had a PMOS current source which was also buffered like this, right? And this fellow basically is supposed to behave like a current source. That's all you wanted. Okay, so here if you see, this is basically in which kind of a configuration? That is, you know, three configurations for, I mean, common source, common drain, common drain. What is this? Common source, okay. And this is a current buffer. It's a common gate, right? And this is how we are making the cascode, putting the common source and common gate together, right? And in this example, we see that common source is made using an NMOS. And same is the case with the common gate, right? So just like how you can make a common gate with an NMOS, you can also make a common gate structure with PMOS. Okay, so you can also make a common gate with PMOS, right? So we have just seen this portion where we use NMOS for the two, Now we'll see what happens if we use NMOS for common source and PMOS for common gate. Okay, and of course you will have you can use PMOS here also, right? So basically you have 4 combinations. We already looked at one. We look at the second case. The other two will be just dual of this. Okay, and to remind you, a common gate with NMOS is made like this. Gate is at incremental ground. The current is applied at the source and the buffered current is taken from the drain. So with the PMOS we do the same thing. The input current is applied at the source, output current is taken from the drain. Okay, so let's say we start with the NMOS common source here. So now I want to take this current and buffer it using a PMOS common gate, right? So this is the PMOS common gate, right? I'll do something like this. Okay, and so that basically finishes these two guys. Now at the load side I need to have a current source which I want to realize using another cascode structure, right? So here what kind of a cascode do you think I should use? I mean, using an NMOS or using a PMOS? NMOS? Okay, I mean, if I were to use a PMOS, how will I use it? See, if I can't do it like this, right? This will not work obviously, right? Because here it will look like we have 1 by GM kind of structure. So I'll have to use an NMOS structure. Okay, so the current source here I'll realize using a cascode NMOS. Is that fine? So here is where I'll apply the incremental input and I'll take the output here. Now of course I need to have these transistors biased at some current. So let's say this is the supply. I need to have something here, okay, because finally current has to be drawn from the supply, right? And whatever you add here, that should be such that the incremental current from this transistor completely goes into this transistor and not up. So what do you think I should put here? I need to have something to bias the transistors. Yeah, PMOS, or ideally what do you want to put? Some current source is what you have to put there, right? So you have the transistor here the current source here to bias the transistors, and that's it. Okay. So this structure is called a folded cascode. So as of now there seems to be no motivation for us to actually do this, right? We already have a cascode made using both NMOS and using NMOS and NMOS. Now just for the sake of curiosity we seem to be doing this, right? So and it turns out this indeed has some advantages. Okay, so besides teaching you guys some new circuit, this actually has some advantages. We'll see that. And that's what you do in practice also. If you have something new, first you don't know whether it is great or not unless you try it, right? You try it out and then you see if it's worth it or not. Okay, so let me label these M4, M6 and M8. Now if the input here is an increment delta V, what is the incremental V out? Can someone tell me? How will you find it? What is the incremental current in the transistor here? So what is the current flowing up? Minus GM2 delta V, that basically has to flow into the output impedance here. What is the R out here? Remember, looking down you simply have the old cascode, there is no difference. Looking up also you have another cascode, right? Please remember, with respect to the small signal behavior, there is no difference between an NMOS and a PMOS. Okay, so looking down, what is the cascode impedance? GM6, R06, R08. So that in parallel with the cascode looking up. So here the cascode device is this fellow. So intrinsic gain of this times the R0 of this. So that is R0. Okay. So the gain you have is similar to what you have in the telescopic cascode structure, right? And that should not be surprising because it's the same cascode, just packaged in a different form. That's all. Okay, great. So now that we have made this single-ended version, let's quickly form the differential equivalent. So, oops. So I need to have a differential version. So I'll start with an NMOS differential pair. Okay, so this is the NMOS differential pair. Now I'll have to take these currents and buffer it using a PMOS common gate. Right? And then at the load side I need to have, what should I put here? An NMOS cascode current source. So we'll just have the same, that's it. And at the top I need to have the current sources for biasing, so let me finish that also. Fine. So let me quickly label these M1, M2. Okay. So say this is a current I0 for the differential pair. So let's say I want to have these two branches to be biased at a current I1. What should be the value of these current sources? This current is supplying currents to which all transistors? Let's say you take the left one. This current, where all does it flow to? It flows to this branch and this branch. So what is the total current it should be providing? No, I'm saying I want this branch to be at I1. I0? See, the current flowing in this branch is what? I0 by 2, right? So the current value should be I0 by 2 plus I1. Okay? Both of them should deliver the same current. So we'll just put in between. Great. So now this is the, I'll take the output from here. So again, I'm wasting the output from one of the branches. So what do you suggest we do? I mean, what have been doing for the other op amps? Sorry, we need to make a diode connection to mirror the current instead of wasting the current from that branch. So where do I make the diode connection? I've labeled it. This is M7, M5. Yeah. You can label, tell the gate of this transistor or source of this transistor and so on. So let me write it properly. Maybe it's not clear. This is M5, M6, M7, M8. Okay. So where should I make the diode connection? For the NMOS or the PMOS? NMOS, right? So from where to where do you suggest I do it? Where do I do it? M5? Drain of M5 or gate of M5? From here to here. Is that fine? If you recollect, this is the same thing we did for the PMOS, right? So for the PMOS, we had the same cascode, and then we took this and connected it here, right? And again, the idea is same. We try to compare. Let me do it. One more. Yeah. So the idea is to generate this bias voltage. Sorry, I erased it. And we'll generate it by comparing the current flowing in this branch with the current flowing in the NMOS branch. And the same usual, same old. So if this current, say Ix, is greater than the current Iy, you want to increase the current Iy, and you can do that by increasing this gate voltage. And when Ix is greater than Iy, this node will increase, so we'll go and just connect it like this. That's all. You can also do the other one, right, as we saw in the last class, but again you will suffer from a limited swing. That's all. Okay, great. So now we have this new folded cascode op amp. So we'll do the same calculations we have been doing for the other op amps. So first we'll find what is the DC operating point. We'll find the gain, common mode range, and slew rate. Okay. So now how is the operating point here? So what are the currents flowing in these transistors? Again, it will be split equally. Now again, although this is asymmetric, you can again argue by contradiction and find out that these two guys will be at the same potential. So if I call this VD3 and this to be VD4, we'll find VD3 will be equal to VD4. Okay, and what will this be equal to? VD3. What is setting the drain voltage of this transistor M3? It is basically the connection we have made here, right? The gate to source voltage of M7. Yeah, exactly. So this should be VGS of M7 biased at a current I1. Okay. Great. So next let's look at the incremental gain. Again, we'll assume that we have inputs V1, V2, and we'll try to find the short circuit GM and the output impedance. So for short circuit GM, I'll go and short this guy, and I want to find what Iout is. So we'll again quickly reuse the results we have derived. So this drain is short, and what is the impedance looking here? It will be 1 by GM of this transistor. Fine. 1 by GM7, so that's also roughly at a low impedance. So this portion is approximately symmetrical because this drain is also short, this drain is also at a very low impedance. So roughly the structure is symmetrical. So then what can you say about this voltage? It will be the average of the two, we had already computed. So if I call the incremental current here to be I1, what is I1? GM1 times the gate to source voltage, which is basically fine. So of course this current will flow here also, I1, right? Now this current is basically sourced from this branch, so it will come like this, right? Okay, and this portion is basically a current mirror. Whatever current is flowing here will also get mirrored. So the current flowing in this direction is also I1. Now you have the current I1 that is flowing here in M2. So what will happen? That will also flow like this, and that will do this, and from here it will enter like this. Okay. So it's the same thing as we have been having all these times. So I out is 2 times I1. So what is the short circuit GM? GM1. Okay. Again, it shouldn't be surprising, right? We the common source structure we have is still this guy. This is the differential pair that is sensing the differential voltage and generating the current. The only thing we have been changing all these time is the output impedance. Fine. So if this is clear, let's move on to the output impedance. Great. So again, for finding output impedance, you will find the looking down impedance, looking up impedance, and so on. But I will not go through the detailed calculation. We know from our past experience that finally the expression turns out to be the output impedance of 1 differential half, right? So we'll directly try to write it. So let me draw 1/2 of the circuit. So you have at the bottom you have M8, you have M6, M4, and then M4 you have the connection to M2. Okay, so this is M2, M8, and that's it. Okay. So what is the R out now? Same thing. So GM6, R06, R08 in parallel with GM4, R04, R02. Great. So now here these current sources will be realizing them using transistors. And what kind of transistor do you think we'll use here? I mean, how many transistors do you know? How many types of transistors? NMOS and PMOS, right? So yeah, what will you use? PMOS. Okay. So I'll do this. So I'll call this M9 and M10. Okay. So now again, if you see earlier we had an ideal current source here, so this portion was open, right? So now you will have the additional transistor M9 and M10 loading here, right? In the single-ended picture also, right? Because now you have this entire portion as the single-ended. Okay, is that fine? So now can you tell me what will be the new output impedance?
Sir,
Yes.
but when we are finding out the Vx, V1 plus V2 by 2, we assume R0 by is to be very high.
No, when you find
R0, that's why we get 1 by Gm, and we assume that impedance is low, so they are on same potential.
exactly. So there the experiments are different, right? To find the short circuit GM, the output is shorted, right? So this is not how you finally operate the transistor, right? Just for calculation, this is shorted. Only in this case, this is equal to V1 plus V2 by 2. Fine. For finding the output impedance, we don't do anything to the output, right? We directly apply some test voltage. We apply some test voltage here and then find what is the current it draws. Okay. There V1, V2 is not there at all. That fine? For finding the GM, it is just a short circuit GM. So there I have to short the output and find what is the current comes.
So why we assume like that?
Why are
they are on low impedance? You told now. We out this part and this part at low impedance. So we assume that this is symmetric.
Correct. I mean, in this case, when you're shorting the output, these two are approximately at low impedance, then we can say they are symmetric. Yeah. I mean, I didn't follow your question. Can you repeat again?
I was confused here. Why you assume like previously you also assumed like something same like that, but I did not understand at that time.
Okay. See, if you had a purely symmetric, let me probably do it again here. If the circuit was purely symmetric, right? And then I had this, something is connected but they are identical, let us say. Then the voltage here is due to both V1 and V2, and then you can find out what they are, right? Because now let us say if the drains here are at low impedance, approximately low impedance, then the looking up what is the impedance? 1 by Gm. So if you see due to V1, you will have this transistor loaded by a 1 by Gm resistor.
But 1 by Gm is less than the R0 is high.
Not, I mean, the drain should be at a low impedance. That's what I'm assuming, right? See, if you have this connection,
it doesn't depend on R0.
What do you call as R0?
I mean, output resistance of
RDS.
RDS.
Yeah, I already asked you to derive, right? You will find that if the drain is at a low impedance, see, the condition turns out to be if the impedance at the drain, if it's smaller than RDS, then this is 1 by Gm. In the first class, I asked to work it out. And in this case, the drain resistance is 0. RD is basically whatever you have here. Okay. And in this case, I'm assuming it's roughly at 0, so this condition is satisfied. In that case, I can call this to be 1 by Gm. Then it's okay? Clear? Okay. Cool. So yeah, let's get back to the output impedance. So here, as I was telling, you have this additional transistor here. So how does the output impedance change? That's all. Okay. Looking down, nothing changes. Looking up, the cascode is still M4, but the resistor it sees is basically the parallel combination of these two. That's all. So this basically changes to GM6 R06 R08 in parallel with GM4 R04 times parallel combination of this. Okay. So now we see that the output resistance has slightly reduced compared to what you had in the telescopic cascode. So there you didn't have this additional term, parallel combination. Okay. So the gain might be slightly lower, but it is still of the order of gm r naught square. Oops, I think I should write this. Okay. So now it looks like the gain is slightly dropped and you need to burn an additional current I1 in this branch. So it seems like everything is everything seems to be negative for this folded cascode. But it turns out to understand its advantage, we'll have to look at the other two aspects. So what is the third thing we'll have to calculate for the op-amp now? Yeah, the common mode ranges at the input output. So let's do that. So let me quickly paste this fellow. Great. So let's calculate the common mode range at the input and the output. So what is the minimum the input can go? The input is here. If I keep reducing the gates, which transistor? Okay, I'll replace all of them with transistors. Hold on. Yeah, just give me a second. Let me. This is M0, and here again we'll have all transistors. M9, M10. Yeah, so if I keep reducing the gates, what happens? The source voltage will drop correspondingly and this transistor goes out of saturation. So what is the minimum you need to have? Yeah, so it will be overdrive of M0 at a current, overdrive of 0 at a current of I0 plus gate to source voltage of M1 or M2. I'll just say M2, the current I0 bit. This is at the lower side. Cool. So now if I keep increasing Vi, what limits the maximum input? If I keep increasing this gate voltage, what might come out of saturation? M10. M10 is this guy, right? No, this is drain, right? If I keep increasing this fellow, I mean drain is, let us say, fixed, it doesn't change. And by the way, first see, I mean with respect to the saturation region calculations, only gates and drains matter, right? Okay. So if I keep increasing the gate voltage, NMOS transistor will start to enter triode, so this guy will have issues. Okay. So what is the maximum it can go? If I call this drain voltage as VD1 and say this is VD2, what is the maximum it can go? It is the drain voltage plus a threshold voltage. And what is fixing this drain voltage here? Yeah, if I call this as VB4, what is this drain voltage now? VB4? Yeah, so it's VB4 plus VSG of M4. Okay, just hold on. VSG of M4, sorry, at a current I0, sorry, what is the current in M4? I1, okay, plus VTH2. Fine. Again, please remember the drain voltages of transistors don't get fixed automatically. We'll see later, if you don't do anything, we'll have to set it ourselves using some mechanism, or it needs to be set by some gate to source voltage like this, right? Because for MOSFET, the current dependence is majorly due to VGS. The current will not fix the drain to source voltage. Okay. Okay, so this is the deal for input, and again VB4 will have its own ranges. We'll come to that in a while. So now let's look at the swings at the output. What is the maximum the output can go? Okay, so if I keep increasing output, which transistor starts to enter triode region? M4. So what is the maximum Vout can go? VB4 plus mod VTH4. Is that fine? And I mean, what is the maximum VB4 can take? Again, if I keep increasing VB4, this what will change? Which one? VD2 will increase because the gate to source is fixed, and if VD2 increases, what will happen? This guy will go into triode. So what is the maximum VB4 can take? VDD? Overdrive of M10 at a current I0 by 2 plus I1. So what is saying is this guy VDD minus overdrive, that is the minimum or the maximum drain voltage can take. On top of it, we need to have minus or plus. Source is at VD2 minus VSG at a current I1. So what is Vout max now? Can you work out and tell me what is Vout max? VDD minus V overdrive of 10 at a current I0 by 2 plus I1 minus overdrive of 4 at a current I1. This is something we saw in the last class also, right? As I mentioned, if the gates are all independently connected, independently available for you to bias it at any voltage, this basically VDD minus these two overdrives, that's all. So in this case, this gate is independently biased. This is also free for you. So the maximum you can swing is VDD minus overdrive of M10 minus overdrive of M4. That's what you get here. Okay, so how about the minimum? So what limits the minimum output? Yeah, here you'll have to be slightly careful because of the diode connection, but again it turns out like that. So if I call this to be VB6, minimum it can go is VB6 minus VTH6, minimum, right? So it's minus. And what is the minimum of VB6? It has to maintain one gate to source voltage to carry the required current. On top of it, a minimum drain to source voltage. So that is basically VGS6 at a current I1. So what is Vout minimum? It's basically V overdrive of 6 at a current I1, V overdrive of 8 at a current I1. Again, in this case, it turns out it's just these two overdrives, that's all. So let me just copy paste this guy. Let's copy. Great. So now let us say these are the ranges for input and output independently. So let us say we put it in unity feedback. So that will enforce this condition. So we'll find what is the minimum and maximum we can go, right? So we have two minimas. So the final minimum will be maximum among the two. So this is the Vi minimum and Vout minimum is this, and we have found that to be equal to this guy, right? So which of these two is higher? One end it is VGS plus V overdrive, VGS plus overdrive. The other is basically two overdrives. So which is higher? VGS plus overdrive, right? So this is the thing that finally determines. So this is basically VGS2 at a current I0 by 2 plus V overdrive of 0 at a current I0. Great. So then let's look at the other end. So let me erase this and write it normally. So on the maximum side we have this fellow and this. So which is, we have to find the lower one or the higher one? Lower of the two, and which is lower among these two? It's obviously clear, this guy, right? And here it is, you see that it is limited by the output maximum, okay? And we already know what is the output maximum, right? Which is this is basically same as this guy. Let me put it in a different color so that it's clear. Okay, so the maximum you can, oops, oh, I'm just doing X again and again. Yeah, so the maximum we can go is VDD minus overdrive of M10 at a current I0 by 2 plus I1. Is that fine? So now if you try to find the range of the voltages we can have in unity feedback configuration, so I'll take the difference between maxima and minimum, and that's roughly VDD minus 1 overdrive, 2 overdrive, 3 overdrive. Okay, I have 2 overdrives here, 1 more overdrive here, and a VGS here. I have roughly written it like this. And let us say I have a supply of 1.2 volt, and say my threshold is 0.4 volt, and I choose overdrives to be 50 millivolt. What is this range equal to? I mean, these are typical numbers you will find in circuits. What is this range now? Say 1.2 minus 3 overdrive is 0.5 minus 0.45, correct? I mean 3 times 50 millivolt is 0.15. VGS is threshold plus an overdrive 0.45. This is what? 0.6. Okay. So, but in the earlier case, if you see, we had only 0.35 when we just had the telescopic cascode. Okay. So roughly close to 2 times you have higher swing here. So that is one advantage with this folded cascode structure. So oops, what happened? Yeah. So folded cascode offers it has better swing, especially when you put it in unity feedback. Okay. So not just that, if you actually look at the maximum input voltage, the maximum input voltage is this, right? And we also know what is the maximum for VB4. So let's put in all these values and see what we get. Let me quickly copy this if I can. So this is VI max, and we also know what is VB4 max. So using these two, what is VI max? So I'll substitute for VB4 first. It's VDD minus overdrive of M10. I'll not write the currents for simplicity. Minus I have a VSG4. This is VB4. And then I have plus VSG4. Fine. I mean, I've just taken the value of VB4 here and put it here. Because I'm trying to find what is the maximum I can have at the input. I'm also putting the maximum of VB4. So this is equal to VDD, these two cancel, minus V overdrive of M10 plus VTH2, right? And again, if you put typical numbers, this will be say 0.4 volt, and this can be as low as 50 millivolt. So this can actually go beyond VDD. Okay. So this is another advantage with this folded cascode. So the input can be at VDD, and this is when you use this NMOS folded cascode. Okay. Now similarly, if you have a folded cascode starting with a PMOS differential pair, where do you think what do you think the input, where do you think the input can be close to? With an NMOS case, I am saying the input can be equal to VDD. If I have a PMOS case, it can be equal to ground actually. Okay. So we can see that quickly and finish it. So we'll try to draw a PMOS folded cascode. So actually, can someone help me draw it, or can someone come to the board and draw it once? Anyone? I'll show the NMOS cascode, folded cascode. So I have it here to the side. Now I want to make a PMOS folded cascode. So which means this guy is PMOS, that's all. Someone? It's okay, rest of the class and I will help. I should announce bonus marks for this. Then it will come.
Simply just give it to me and we want that.
Yeah, come. Yes. Yeah, come give it a shot. Yeah, you can use the side of the board. No, you have to have a PMOS common source, right? So the source must be that's a very unconventional. Usually source comes at the top. Okay, and source, if you ground it, PMOS will not work properly, right? So source should not be ground. It should be at a common source. Huh? Yeah. Others help, no? What should you do? Draw in a conventional way. Source comes at the top. Else it becomes difficult, right? Because source should be at higher potential. So can someone help him? Huh? No, no, you try, it's okay. You started right. You started right. You draw the source at the top.
Okay.
I mean, first of all, draw PMOS differential pattern. That's enough.